I'm going to describe how an absorption column works and then write down the mass balances that we use in order to determine the number of equilibrium stages. So the general idea is we feed a vapor phase that has a concentration of an impurity, a solute, that we want to remove. So we want the exit vapor phase to have much less of that solute. We remove it by contacting the vapor with a liquid phase in stages. So the liquid phase is fed with a low concentration of that solute and leaves with a higher concentration. So notice that the ratio of the liquid flow rate to the vapor flow rate for this particular example is 100. So of course the liquid's much more dense, so we expect the molar flow rate to be much higher. For this example, and for this case, we're going to use these values as mole ratios. So they're very close to mole fraction because the concentration of solute is really quite low. So if we look at a column with 5 stages, you can see that the concentration, 59 in the gas phase, decreases with each stage, whereas the concentration, 0.05 in the liquid phase, increases with each stage. Now notice this corresponds to 59 mole per hour being fed of the solute, and we multiply by 10 to the 6th. And this corresponds, because the flow rate is 100 times higher, 54 moles per hour to solute. So we're removing approximately 95% of the solute that's in the vapor phase. So let's look at the mass balances that we use to analyze this type system. So on this diagram for mass balances, we'll call this X0, and then mole fraction or mole ratio in liquid phase. The subscript corresponds to the stage that it's leaving. And likewise for the vapor phase, the subscript, so we'll use Y vapor phase mole ratio. The subscript corresponds to the phase that is leaving, which means this is Y6. So if we look at the nth stage, then the mole ratios leaving, Xn and Yn, these values are in equilibrium. That's what we're assuming in this analysis. Because such low concentrations, parts per million in this case, we will model this by Henry's law and say Yn is equal to Henry's law constant over pressure times Xn. So Henry's law constant in this case has units of pressure. There are different ways of defining Henry's law constant. And so let's look at a mass balance for this part of the system. And if we're going to do now a mass balance on the solute, we're essentially saying solute flow in equals solute flow out. Flow in is X0 times the liquid flow rate plus Y4 times the vapor flow rate. And what's leaving then is X3, liquid flow rate, plus Y1, the vapor flow rate. We can do a balance for any number of stages, just 1 and 2 or all 5. And so the general form of this equation is Yn plus 1, because remember this was stage 3, Xn times L plus Y1 times V. So that just rearranged the equation, and this is what we're going to call the operating line. And so if we want to determine the number of stages, we're going to plot the operating line and the equilibrium line, and then we'll step through how we do that calculation to determine number of stages. So apply to some example values. This is the equilibrium line, Henry's law, so it's linear. This is the mass balance line, the operating line, and that's this equation here. And I picked a value for Y6 of 21. So that has to be on the mass balance line. And the way we determine equilibrium stages is that if this value here is Y6, this value then is going to be Y5 and X5. Because X5 and Y5, the values leaving stage 5 have to be in equilibrium, so they need to be on the equilibrium line. Well then, for the mass balance, This point is X4 and Y5, because X4 and Y5, you can see here is where we do a mass balance. We do, say, a mass balance around this. They have to satisfy the equation. And then we can step through. This is still X4, but now it's Y4. And of course, X4 and Y4, leaving stage 4, have to be in equilibrium. And we can continue, and doing this by hand, of course, is not as accurate as if I was a little more careful, but I can do this into, here is X0. We don't have another stage. Here is X0 because that's what has to be on the mass balance line, and it corresponds then to Y1. Right? That's the feed and liquid phase coming in, and we can count the stages: stage 3, stage 2, stage 1. So this is how we can step off stages, determine number of equilibrium stages required for a certain separation in an absorption column.